Today's presentation is titled Machine Learning for Medical Imaging Data Analytics and will be delivered by Dr. Yong Fan. And then Dr. Fan is an associate professor of radiology at the University of Pennsylvania, Perelman School of Medicine, a specialist in machine learning and computational imaging. Dr. Fan's work focuses on integrating multimodal data to enhance diagnostic precision, optimize predictive modeling, and guide personalized therapies. His research spans neuroscience, oncology, and nephrology, particularly in brain aging, neurological diseases, and cancers. His innovative methods, supported by the NIH and the Pennsylvania Department of Health, include functional connectomics, radiomics, and personalized neuromodulatory therapies. Dr. Fan's work also explores deep learning and self-supervised learning to reduce dependency on labeled data sets in medical imaging. Today's presentation will highlight deep learning's applications in early disease prediction, including Alzheimer's and lung cancer. Dr. Fan will discuss the role of interpretable machine learning and self-supervised model in medical imaging, especially for data segmentation and predictive modeling of brain development and psychopathology. We are pleased to welcome Dr. Fan, and whose expertise and insights will deepen our understanding of the transformative potential of machine learning in medical imaging analytics. Dr. Fan, the floor is yours. Thank you.
Yes, thanks so much for the kind introduction. So it's really great pleasure to introduce our research done before and recently. So my research focuses on machine learning for medical imaging data analysis with different applications to studies of neuropsychiatric disorders, neurodevelopment, brain aging, cancers, and neurological disorders. So here is my research lab located in Research Building on the top floor. So we have a dry lab in this building. So this campus is quite beautiful from the overhead view. So here is some kind of research topics. We are working in our research lab. We develop image analysis algorithms for image segmentation, like brain tissue segmentation, cortical surface reconstruction, and abdominal organ segmentation. We also develop methods for image registration using deep learning and using conventional computational tools. We also work a little bit on smart image reconstruction, try to use deep learning techniques to improve the image reconstruction for speed up MR data collection or to reduce the dose for CT imaging. We also use deep learning to model electronic fields with applications for precision TMS delivering. So we could use TMS generated electron field combined with structured MR data. We can accurately calculate the electronic field induced by TMS in the brain. One major focus of my research has been on functional network modeling. We developed personalized functional network modeling techniques with different applications like brain development, brain aging. So we also try to expand the research into studies of Alzheimer's, depression, all kinds of psychiatric disorders. So although we developed all kinds of machine learning models for early prediction diseases or try to predict the treatment outcomes for lung cancer patients. We also developed image processing and predictive modeling techniques to aid the diagnosis and prognosis of neurological disorders. So in this presentation, I'll focus three different items, including self-supervised learning for image processing, like image registration and image segmentation. Then I'll introduce some of our recent work related to interpretable machine learning to model functional network measures. Finally, I briefly go over through some our earlier work using deep learning to build prediction models for early prediction for onset Alzheimer's. A similar idea can also be applied to early prediction for clinical outcomes for lung cancer patients. So I don't know if you are familiar with all kinds of image processing, especially for neuroimage data analysis. So we need to do image segmentation, we need to do image registration so that we can use statistical analysis techniques to analyze statistical effect of a group of subsets. So many excellent algorithms have been developed in the past decades, but traditional image processing methods are computationally inefficient. It takes probably like for image registration, it takes about 20 minutes or even longer for cortical surface reconstruction using free surface. The total computation can be up to 10 hours. So it's really slow for real-time applications. Of course, for data analysis, if you don't have a large computing cluster and you have a large number of scans, so the traditional computation methods are not very efficient. So, of course, to speed up the computation, many deep learning methods have been developed. Most of them are developed within the supervised learning framework. So, for example, if you want using the supervised deep learning framework, if you want to develop a segmentation model, you have input image, you have a model to be optimized. The model can generate a segmentation, but to optimize deep learning model, you need to have manual labeled information or labeled image generated by other types of methods. So basically, you need to have supervision information to add or to optimize the deep learning model. So sometimes it's difficult to generate manual label data, and if you use other types of automatic methods, your deep learning model will be biased to those kind of methods. So, but for I'll try to give another example for image registration. So before deep learning, we don't need to training data, right? We can, for image registration, if you have two images, you just want to generate a deformation field by optimizing the similarity loss. So basically, you can use iterative optimization algorithms to optimize the deformation field. But if you try to use the supervised deep learning to build a deep learning model, so you need to have a guidance of the deformation field. So of course, many earlier works try to use conventional or traditional image registration algorithm to generate deformation field, then build a deep learning model to predict that deformation field. So we think we can directly use deep learning based predictive modeling strategies in conjunction with traditional image similarity optimization framework. So basically, we try to build a deep learning model. The deep learning model can generate a deformation field by optimizing the image similarity. So this idea quite simple and straightforward. Basically, we just combine deep learning based predictive modeling with traditional image similarity based optimization. So I think this kind of very early work for self-supervised deep learning in terms of image registration. So after that, we try different strategies to improve the image registration performance, such that we can improve the image registration accuracy and efficiency using multi-resolution strategies. We can also using network architecture searching techniques to optimize or improve the network architectures. And we can also use different strategies to improve the diffeomorphism of the image registration results. Here I just show you some results we obtained using the multi-resolution based image registration algorithm. We compared our algorithm with other types of deep learning based and traditional image registration algorithms like native-reg, ANTs, this Voxmorphy, and the two other types of deep learning models. So basically, quantitatively, our method can get improved image registration accuracy, and the diffeomorphism of the image registration result can also be improved. So actually, the same idea can be applied to brain tissue segmentation. So I don't know if you are familiar with brain tissue segmentation. So the basic or the most kind of simple algorithm can be developed based on k-means based clustering. So basically, you can directly use k-means to cluster the voxels based on the intensity information. So that's a traditional method and very robust, or you can also use a kind of improved versions of clustering like a Gaussian mixed model. So basically, you don't need two training data. But here, we also basically we try to combine deep learning with conventional Gaussian mixed model based modeling to build a deep learning model to directly generate tissue segmentation results. So here, we also try to highlight to make the deep learning model robust to any image. Most of the deep learning models are applicable just to bias corrected image, but that step is really time consuming if you use conventional techniques. So years ago, we developed a method we try to combine both the bias correction and Gaussian mixed modeling together in conjunction with deep learning based prediction model. So basically, we can develop the unsupervised or self-supervised deep learning model to generate brain tissue segmentation results. So here are some kind of representative results of the brain tissue segmentation and bias-based correction results using conventional method and using our deep learning method. So here you can see, so visually our method, the results generated by our method is quite similar to the free server result. So here we use the free server result as kind of ground truth because that algorithm is widely used to process the ACP style data set. So we also did some quantitative comparisons based on different data sets. Actually, you can see that self-supervised deep learning models is robust and generalized well to different data sets. Here we train a model based on the ACP agent data set. Then we evaluated the model based on the ACP development data set, all the data set and Yong data set. So basically, we can see the generalization performance is quite good. Our model could achieve better performance than conventional techniques like FSL, the fast algorithm, and the Atrops algorithms across different data sets involved in the training and not totally new to the training data set. So if you have any questions, just stop me. So here I try to switch my gear to functional network modeling. So functional network, like using fMRI data, we can characterize brain activity. So to analyze fMRI data, functional network modeling is a powerful method. So basically, we can get kind of compressed measures to describe the brain activity. So for example, from fMRI data, we can compute a large number of functional networks. So those networks, in many studies, have demonstrated are associated with different brain functions affected by different diseases. So many studies also demonstrated that functional networks are actually quite different across the individuals. There's so high inter-subject variability. So this actually is our collaborative study for brain development so basically no matter what kind of method you use, you can always identify inter-subject variability in functional networks. But how can we improve the computation of functional networks? So years ago, we developed a method based on the non-negative matrix factorization. I'll pass a little bit of detail about the method later, but here, so using this method, we can directly optimize two different components or things. So first of all, we can directly optimize the functional coherence of the functional networks, and we can also regularize the functional networks to have some common special patterns so that we can use statistical analysis techniques to investigate group effect or to build machine learning models for different purposes. So this is some kind of evaluation based on all the results in our studies. We have demonstrated that this method can better delineate personalized functional networks in terms of functional coherence, also can generate functional network connectivity measures that are useful or informative for predict brain age. And we can also compute functional networks based on resting state MR data, but those networks are highly aligned with functional networks computed from task fMR data. So this method has also been used to build brain decoding models using recurrent neural networks, and the functional networks computed use method has been used in large number of brain development, brain psychopathology studies. In all these studies, we have demonstrated that the personalized functional networks computed using this method is really useful, can provide useful information for characterizing brain development, sex difference, or psychopathology. But how we can compute the functional networks? Mathematically, actually, is quite simple. We just need to do a metric decomposition. For example, here we have fMR data. fMR data is kind of 4D data. We have 3D spatial information and one-dimensional temporal information. So, but for traditional metrics decomposition-based method, we need to convert the 4D data into a 2D matrix, then use a low-rank-based metric decomposition to identify functional networks and related function time series. So, but for I don't know if you are familiar with RCA or types of methods. That's the most popular method used for computing large-scale functional networks. But that assumption is kind of problematic because many functional networks actually have kind of overlap in terms of functions. So if the assumption is built up is relatively dependent, so that's a kind of a violation with real data. So we instead use independent component or use independence based assumption. We directly use a non-negative metric factorization. So non-negative factorization actually is closely related to k-means based clustering. So that's the reason our method can compute functional networks with improved functional coherence. So, but when you try to use this kind of method to analyze fMR data from multiple subjects, you need to take take care about the special correspondence of functional networks computed from different individuals. So to solve that problem, we use different kinds of special regularizations. For example, we can use group sparsity regularization to regularize the computation of multiple subject functional networks. But how we can solve this mathematical problem? So basically, you need to use kind of EM-based diagrams. You generate a random initialization solution, then compute one part of the parameter like U, then base more compute U, then we can compute V. So basically, you need to use iterative optimization algorithm to solve this problem. It's really time consuming, and the solution is purely based on your initial solution, and you can just get a linear solution that's probably not very good in terms of what we developed compared to deep learning based method. So here, because you can see to solve that optimization problem, we just have a data fitting term. Of course, we also have additional regularization terms. So using deep learning, actually, we can directly optimize this data fitting term. We can use build deep learning model to directly generate those personalized functional networks. Here, so basically, we just do some simple mathematical inference. We can convert this data fitting based on loss function to this format. Then we can directly build a deep learning model to minimize loss functions, then to generate personalized functional networks. So this for any machine learning models or deep learning models, the first thing you to evaluate the generalization performance. We train this model. We train a model based on HCP data set, then apply this model to different other data sets. Like here, we just show the performance when we apply the HCP model to the PNC data set. So HCP data is Young adults data set. The PNC data set is a brain development data set with kids from 8 years old to 21 years old. So here we show some representative results. We can see the kind of inter-subject variability, and we can also have some kind of quantitative results to demonstrate that deep learning-based methods can generate personalized networks with improved functional coherence. And also the functional networks can provide useful quantitative measures for predicting brain age. So we also use the permutation test to evaluate the statistical significance of the prediction accuracy. So that's a kind of application of brain development study. The method has also been evaluated for different distinguished schizophrenia patients from normal controls. Again, we apply the HCP model to the schizophrenia data cohort. We get subject-specific functional networks. We build a classification model to, again, the functional coherence is just a kind of quantitative measure to evaluate the quality of personalized functional networks. And we also build a classification model to distinguish patients from control. So basically, all those results have demonstrated that the personalized functional networks computed using deep learning can provide useful information. So, but we also try to extend this method to compute functional networks at multiple scales with kind of hierarchical organization, because many existing studies, including ours, have demonstrated the brain is a hierarchical multiple scale system before we can just apply our method to the fMRI data with different settings of the number of functional networks. For example, we can apply the model with two networks, 3, 4, or so on and so forth. So basically, the method itself cannot effectively characterize the hierarchical information. So years ago, we developed the deep matrix decomposition-based method. So basically, for matrix decomposition, we can have a series low-rank matrix to achieve a kind of hierarchical decomposition. Again, the computation cost related to this method is really high. You need to, again, use the iterative method to optimize this method, mathematical problem. So use a similar idea, we build a deep learning model to directly optimize the loss spikes, and then we can generate functional networks at different multiple scales. Here we try to show some representative results, including the group average results and functional networks from different individuals at different scales. Basically, we can see the individual subjects have a certain variability in terms of the location and the extent of their functional networks. And quantitatively, we can also find that individualized functional networks have better functional coherence compared with the group level components or functional networks. So besides the functional networks themselves, the method can also provide quantitative measures to characterize how different networks at different scales interact with each other. So for example, we can have personalized hierarchical organization information, and we can also group means to characterize all the functional network organization. So this kind of quantitative measures actually are also very useful for characterize brain development I can show later. So here are some examples to better illustrate inter-subject variability in terms of network organization and hierarchical. So you can see this is how the high-scale functional networks merge to form coarse-scale functional networks for 3 different subjects. Their connecting patterns are slightly different. So we found that those differences actually are useful for predicting, like for distinguish males from females, and also useful for predicting brain age or distinguish schizophrenia patient from health controls. So in all those studies, we use conventional or traditional machine learning techniques for building classification model and prediction models. We also integrate most of our algorithms in a toolbox so that we can provide some solutions readily usable. So at an early stage, we developed this package using both MATLAB and Python, but starting this year, we abandoned the MATLAB version, so just focus on Python-based development. So here, I try to give a small summary about the self-supervised learning. So basically, our research has demonstrated that self-supervised learning is kind of useful. Basically, you can combine deep learning techniques with conventional or traditional medical image processing techniques to get improved deep learning models with after relying on any external supervising information. So this we use this strategy to solve the electronic field modeling techniques, and we also extend this method to generate weakly supervised deep learning models. So, for example, to generate segmentation models that can be segmented many different abdominal organs, we combine multiple data sets, public data set with partially related data. So then using some computational tricks, we can make the model robust because the training data is from resources with diverse information or images were collected with different scanners at different sites. Probably those images are affected by different diseases with varied severity. So next, I'll try to highlight something we developed recently for interpretable machine learning. So here, we try to highlight that, so using functional network modeling techniques, we can generate rich quantitative measures like functional network topology or functional connectivity. But if we want to have a machine learning model or predictive model interpretable, we typically need to use linear models. So although you could use sophisticated deep learning models to build predict models, like before we use recurrent neural networks to develop decoding models, we use convolutional neural networks to build predict models. But to interpret these models, we need to use post-hoc analysis techniques, like sensitivity analysis or a different kind of gradient computation-based method to highlight which features or is useful for the predictive modeling. So, but all those kind of methods are probably not very accurate because the post-hoc analysis techniques are quite different from the original deep learning model building techniques. So recently we try to build an interpretable deep machine learning method. So basically we borrow ideas from neural adaptive models. We try to combine neural networks with linear models to build a kind of interpretable machine learning models. So the idea is quite simple. So basically we can build deep learning models for individual features or individual feature unit. So here we try to use feature unit to have, you can have different definitions for feature unit, for the feature unit. For example, the feature unit can be a single functional connectivity measure, or can be a brain region, or can be a functional networks. Here, basically you can, once you have a definition of feature unit, you can use deep learning model to predict a prediction model. So after you have deep learning models for all available feature units, then you can generate an ensembled prediction model for the overall prediction. So this model is kind of inherently interpretable. So because you can directly look at individual features predictive performance, you can also look at how the different feature units collectively contributed to the overall prediction. So here we show some results to demonstrate the performance of this kind of method. So here we try to use a prediction task for cognition performance to demonstrate the performance of this method. So here we, once you have all those features, you can directly pull all of those features together to build a model. You can also build separate models for different features, then combine them together. But you can also use our method, so build different individual models, then learn a weight to combine them together. So here you can see using our strategy, we can have the best performance. And we also find the weights learned by our method are really informative. So you can apply the weights to, okay, here is a performance of model built on all, by putting all features together. The second model is a model by first build individual models on each feature unit, then use simple average to generate overall prediction of models. And the third one is our method to learn both local or individual prediction models and the weights to combine those models. If we apply those weights to individual models built using other methods, actually we can also improve the prediction performance. So this performance or this pattern is quite robust across different predictive tasks. And here also we also show some the weights distribution and the individual models prediction performance. We can see those weights are closely correlated with prediction accuracy of video model, but there also some kind of a discrepancy between those two weight map or individual prediction performance maps. So we also find this, we call it relevance map, or the weights are kind of generalizable. So we apply the weights to predict longitudinal cognitive measures. We can find those weights is really generalizable from baseline to the 2-year future prediction task. And these weights are also generalizable to different data sets. So this is the ABC, we build a model based on ABCD data set, but apply the model and evaluate the model based on CPD data set. Although the tasks are slightly different, although they all belong to the same category of cognitive performance. So based on those encouraging results, we further extend this method to identify specific heterogeneity of functional connectivity development. So here we just, I don't know if you are familiar with like brain age prediction model. So basically you can build a prediction model to predict brain age based on the brain imaging data. Then you can compare the predicted brain age with clinical or biological age. So those differences can be used to characterize brain development, brain aging patterns. So here we try to use a localized model to highlight how brain development is different across different subjects. So here we use the localized or interpretable machine learning method. We identify 3 different patterns or subgroups of subjects. This one is a kind of lagged development. So the predicted age is smaller than the biological age. And this pattern is related to advanced brain development. That's good thing for kids, bad thing for adults or old people, because the brain is older than the cortical age. That means accelerated aging, not the development. But the most interesting part is the pattern too. So we see some advanced development and delayed development. But when we compare these two patterns directly, we find that the advanced development in pattern 2 actually is more advanced than the patterns in pattern 3. So we found that those regions are quite interesting, closely related to cognitive performance, like decision, cognitive cortex. We generated results using automatic and meta-analysis. And we also directly compared the cognitive performance across those three different subgroups. We found that the pattern 2 has the best overall cognitive performance in terms of executive function, memory, and social performance. We also evaluated this finding by correlating the pattern 2 with different types of functional measures like principal components derived from functional connected networks. And we also find that the pattern is also highly correlated with myelin content. So basically, I quickly give a quick summary. Our results have demonstrated that the interpretable machine learning can provide improved predictive performance compared with traditional linear models. But at the same time, that we can achieve better interpretability. So we just demonstrated the performance based on the functional connectivity measure. But this technique is applicable to any types of image features or all kind of quantitative measures. So that's our ongoing research. So finally, I try to give a quick overview of some predictive works we've done before for early prediction of Alzheimer's and some applications for early prediction clinical outcomes of lung cancer. So to be honest, please let me give a very quick overview of the early prediction of Alzheimer's. So basically, for this project, we try to develop prediction models. So typically, this problem is solved in a classification setting. So basically, for early prediction of Alzheimer's dementia, you can build a prediction model, a classification model to distinguish progressive MCI and stable MCI. But to define those two categories of subjects, you need to have a threshold. For example, you can define the progressive MCI based on 2-year threshold. So if a MCI subject remains stable within 2 years, that's stable. If that subject convert to AD, that's progressive. But so the threshold of the 2 year, 3 year, or 4 year may affect the overall prediction performance. So here we try to directly using time to event prediction framework to solve this problem. So we can predict the risk of the conversion, and we can also estimate when the conversion will happen. So the algorithm actually quite simple. We use deep learning to extract the features. Then, based on those deep learning features, we use a standard Cox regression model to build risk prediction models. So in this study, we focus on the hippocampus region, and for the evaluation and the model training, we use any data set. We build a feature extraction model for classification based on a purely any one data set and evaluate the performance based on any go to an AIBL data set. Here is the classification performance. So basically here we try to demonstrate that deep learning features are really powerful for distinguish AD patients from normal controls compared with traditional shape-based features or texture-based features. And we can also use class activation mapping techniques to highlight which image regions contribute to the classification. And we also find those features are highly correlated with cognitive measures. Here, based on the risk scores generated by the prediction model, actually we can do patient subject stratification. So here use any go-to data, we found that the risk score actually did an excellent job to stratify MCR subjects into subgroups with distinctive risks. We can also combine the deep learning-based prediction risk values with conventional or popularly used demographic and clinical measures to figure out which features or measures are more useful for this kind of prediction. Here in our study, we found that the deep learning-based risk, prognostic risk actually is quite robust in terms of prediction. Because in this Cox model, the risk is selected as the most significant features for the prediction in addition to FAQ and IVLT. Those are two cognitive measures widely used in research for Alzheimer's. So we can then we combine the image-based risk score with demographic and cognitive measures. Then our model can achieve excellent C-index value of over 0.86. And we can also use time-independent RC curve to further evaluate performance at different thresholds of years, like year 2 and year 3. So finally, I just listed some of our past studies related to lung cancer. So basically, we use similar strategy to build the prognostic models so that we can early predict the clinical outcomes of lung cancer patients. So here, basically, our research just demonstrates the time to event predictive framework are really useful to evaluate or to predict onset of disease or to evaluate effectiveness of treatment strategies. So this framework might be useful for many predictive tasks related to onset or recurrence of a disease or survival analysis. Our research also demonstrates that quantitative features extracted using deep learning are really useful. So here, probably I have a little time to demonstrate some web app. So basically, in this web app, we integrate the deep learning-based image segmentation model, deep learning-based cortical surface reconstruction model, and the deep learning-based prediction model. So at the beginning, we just combine deep learning-based feature extraction with traditional predictive models. But later on, we build a purely deep learning-based model using end-to-end learning. So here, let me show a demo here. So, okay, it still works. So here is a web app. So I have a lot. So basically, we developed this user interface. If we just show MTY image to the web page, then upload the data to our server. So you can see the computation behind. So we remove the web app can remove all kinds of sensitivity information before data transfer. So basically, we just transfer the voxel intensity information and the geometry information. So the uploading is done. So the computation should be done to here. So we do the computation, including the segmentation, cortical surface reconstruction, and deep learning-based predictive modeling. So pre-segmentation done, so we generated a brain mask remove scar, generate citation result, then building the prediction models. So here start the MCR prediction, so the prediction is done. Okay, I can just load the results. So we get the citation and we also generate a risk prediction. So all within a few seconds. So the server is quite old. So if we have a little bit more powerful GPU, probably can be a little bit faster. So finally, I would like to thank my collaborators, my students. So basically all the research can be finished with after their help. So I have collaborators in methodology development and neuroimaging studies. We also have collaborators from kidney disease-related research project. We have a group of clinicians. They supported our cancer-related research. Okay, thank you so much for your attention.
We have time for some questions. Mustafa?
Yes, thank you very much. That was a great presentation. And I realized that you use linear algebra tools very efficiently to reduce the cost, computational cost. So regarding the optimization problem where you are decomposing that X, I think you're using like a non-negative matrix factorization for that.
Yes.
So I have two questions regarding that. The first question is regarding why NMF over truncated singular value decomposition, because I know that for NMF we are using like a sparse matrices, and they must be like a non-negative. U and V in that case must be a non-negative.
Yeah, yes.
So that means computational experience is going to be cheaper. At the same time, you can interpret them. But when you're using like NMF over T SVD, so for reconstruction purposes, it's going to be worse than T SVD. So this is the first question, why we are using like NMF here. The second question.
Let's answer this one.
Yes, sure.
Don't forget your second question.
Okay. So if you just have one subject, it's cheap to
Yes.
do the computation. But you can imagine that you don't need to have 1,000 subjects. You just have 100 subjects.
Yes.
So you can see, if you just want to have a group level computation, you have a huge matrix.
Yes.
But if you want to do like what we are doing here, subject specific computation, so that's way more complicated. We need to include a large number of regularizations to
Yes.
enhance the special correspondence. So using cluster to generate this kind of group level functional networks with just 100 subjects, it takes more than 12 hours.
Yes.
But using deep learning, you can, once we have that model, we can finish the computation for each individual subject within 4 seconds.
Have you tried truncated singular value decomposition instead of NMF?
No, so because here for functional network modeling, we try to get a good representation of the original fMR data. We don't want to lose any information. Of course, the low rank-based decomposition will always lose some information,
Yes.
but we try to keep original information
Yes.
as much as possible.
Yeah.
That's the reason we use the non-negative matrix factorization. So also the non-negative matrix factorization is closely related to k-means space cluster.
Yes.
So the functional network modeling. So
Yeah.
we want to have those kinds of property.
Yes.
So to evaluate the quality of functional networks, actually we could use like the functional coherence. What do we mean by network? So a network basically consists of voxels or vertexes with similar information. So
Correct.
to evaluate the quality of a functional network, actually you can evaluate how different voxels or vertexes within the same network are similar to each other or different to each other. So that's the reason we use functional coherence. That kind of a measure to measure the similarity between different devices. So use NMF, we can achieve better functional coherence.
Yes.
So I guess it's much better than the truncated support vector machine.
Sure.
SVD. So because those, so basically SVD probably can give you directions of big variance, but
Yes.
difficult to maintain the correspondence across different subjects. So probably different. You can have some kind of networks from different subjects, quite different, that are comparable. That's the reason why PCA probably was the first metric decomposition method used in functional network models.
Sure.
Okay. No one uses PCA.
Yes.
So,
So you mentioned about like k-means, and I'm going to talk about like this structure that you have. I thought that the dimension of that matrix X was like T by N, and you have like an inner dimension of K. So usually for SVD or this, so we have like 3 ways to just decide what that K should be. So how did you optimize that K?
yeah, that's a great question. So actually, to be honest, we don't have a good solution to determine a good number.
Okay.
So basically, we use some kind of information-based theory to generate a good number, then use kind of cross-validation. So we split data, then generate model, then compare different models. If they are consistent, okay, that's probably a good number.
So did you put any like threshold for the like loss function for this minimization? So usually this is going to be solved like based on it like a threshold for the loss. So in that case, you
no, we don't use any threshold.
Okay.
We directly optimize all of data fitting plus some kind of regularization.
Okay. Thank you. I'm sorry.
No, this is great discussion. I really like that. And sometimes just, and I don't know if it applies in this case, there could be a framework like a KK information criterion or something to determine the value of K, which is notoriously difficult.
Yeah, that's related to clustering, right?
Yeah.
So for clustering, probably there are more than 50 different criteria to evaluate clustering algorithm or clustering results. So no one. So basically, we don't have a really good answer. So probably you can even use different information theory-based metrics. You can have quite different answers.
Yeah.
So to determine that number, we have to rely on kind of experience. So for example, the number 17, because many people use that number. So
yeah, that is the answer. Thank you very much. This was an amazing presentation. You very effectively used deep learning to solve some of the hardest problems, and then you also successfully demoed something. Just typically demos don't work when you present. It worked here and then across the class.
Because that project was started.
Thank you very much. This was impressive. Let's thank you again.
Yes, thank you. Really appreciate it.